Okay, here we're going to do work through a problem, and the example is going to be of calculating the electric field on the axis of a charge ring. And this ring is going to have a non-uniform line charge, which depends on phi prime. Again, we've got prime because it relates to the source. Okay, so the first thing I'm going to do is I'm just going to draw a very simple schematic of what we're actually trying to determine. Okay, so there's my axes. The circular ring of radius A lies in the xy plane. It's got this radius A, and it's got this non-uniform line charge, which is given by lambda phi prime, which is equal to A sine phi prime. Okay, so we want to calculate the electric field at some point located on the z-axis. Now, the next thing that I'm going to do is I'm just going to write down that the electric field equation that we want to solve. So we have our electric field. It's going to be equal to 1 over 4 pi epsilon naught. We have a line integral, because we've got a line charge of lambda or prime. Okay, remember the prime is with respect to the source, so we've got or minus or prime to be squared, or a unit vector dl prime. Okay, so the integral, we've got this prime, the integral is with respect to the source. Now, in a similar way to what we did for the point charges, what we're going to do is we're going to work out what our field vector is, which is given by or, and also our source vector, which is given by or prime. So for our field vector, it's going to be along the z-axis and from the origin. Okay, so it's going to be given by z hat. For our source, we have or prime. It's going to be given by s prime s hat. Okay, because it's pointing away from the origin, and it's that this is from the origin. The vector is from the origin to where the line charge is. Okay, so that's s prime s hat. We can write our separation vector s prime s hat, and the magnitude is going to be square root of z squared plus s squared. Now, it's important here to use the prime because the prime, as I say, relates to the source. If we wanted to calculate the electric field at some point displaced from the z-axis, we would not use a prime, we'd only use s hat. Okay, so it's very important to distinguish between the two. Okay, so now that we have this, all I'm going to do is I'm going to put this into our equation for the electric field. Okay, so what our equation is now going to look like is going to be the electric field be equal to 1 over 4 pi epsilon naught by the integral of a non-uniform line charge, which is A sine phi prime, divided by z squared plus s squared by our unit vector, which is z hat minus s hat, s prime s hat, divided by, put these primes in, divided by the square root of z squared plus s prime to be squared. And what are we integrating all over? So what is dl prime? Well, dl prime, since we're integrating around the ring, is going to be given by s prime d phi prime. Okay, so we've got s prime d phi prime. Okay, and now this is what we must solve for. Now what's very important to do here is, since s hat is changing around the ring, we don't know what the direction is. It could be in this direction, isn't going forward, or it could be going backwards. What we must do is to convert it into Cartesian coordinates. Okay, so s hat can be written as cos phi prime x hat plus sine phi prime y hat. Okay, and the reason being is x hat and y hat are constant and constant in direction. Okay, and they can now be taken outside the integral. So what we have is we've got three separate integrals when we put this in for s hat. Okay, so we have our electric field now. Will be equal to 1 over 4 pi epsilon naught by the integral, and I think I should just go back here. The limit on our integral here is between 0 and 2 pi. Okay, so we're going around the ring. Between 0 and 2 pi of a sine phi prime divided by z squared plus s prime squared 3 over 2 by z hat by s prime d phi prime plus the integral to pi, and this is going to be now for our x hat direction. So we have a sine phi prime cos phi prime over z squared plus s prime squared 3 over 2. And this is the x hat direction, and we also have this other s prime in here. So s prime to be squared, it's in the x hat direction, and it's d phi prime. And finally, for the y hat direction, we have a sine squared phi prime (3 over 2) by s prime squared y hat d phi prime. Okay, and now we just have to work out each of these integrals, and we will get our final answer. So when we do the integral with respect to sine, it's going to be equal to 0. Okay, so this will equal to 0. Whenever we do the integral with respect to x hat, it's going to be equal to 0. And when we do the integral with respect to sine squared phi, we're going to get pi. Okay, so the integral from 0 to 2 pi of sine squared phi prime d phi prime is going to be equal to pi. And now we can just write out our final solution. Okay. And also note that S prime is equal to our radius A. So now our electric field (1 over 4 pi epsilon naught) by A pi A squared. So we've got A pi A squared, remember A is the radius, divided by Z squared plus A squared to the power of 3 over 2, and we're in the y hat direction. Okay, so again you can see that we've got no primes left, everything works out, and this is our final answer.